Okay, so we just learned about addition, but we've really only looked at positive or adding positive numbers. So the next thing we need to do is essentially to think about how we can represent negative numbers, right? So what we need is an efficient way to represent negative numbers. So meaning that both positive and negative numbers are effectively going to be strings of bits. We'll use in a fixed width format, so 44-bit, 16-bit, etc. And the numbers must provide an efficient mathematical operation. So we want to do addition and subtraction with potentially mixed signs easily. Okay, so the first representation that we'll introduce is sort of fixed, the sign magnitude representation that's shown here. So the idea here is actually really simple, right? You have numbers, so shown here, and it's just going to say the first bit, the highest order bit, is the sign. If the highest order bit is 0, as shown here, it's a positive number, or 0, and if the highest order bit is 1, then it's a negative number. And in this case of the sort of the 4-bit format here, the 3 lower order bits are the magnitude from 0, 0, 0, which is 0, to 7. Okay? So the number that can range for n bits from plus minus 2 to the n minus 1 minus 1. And there's 2 representations for 0 here, which is a little bit wasteful, but a priori it's not a big problem. So what I'm representing here, by the way, on this circle is essentially all 4-bit numbers sort of in an ordered way, as you would get if you just keep incrementing and turning over. You'll sort of move around this cycle or this circle. Okay, so let's first look at additions in this sign magnitude representation. So the rules are essentially given here. So if the signs of the numbers that you want to add are the same, you just add the magnitudes, keep the sign. If the signs are different, well, then you're subtracting the smaller number from the bigger number, right? So you essentially find the difference, and you keep the sign of the bigger number. I mean, this is just writing down what you would have intuitively have done to figure out how to add these numbers. And just here's a few examples of this, which you might want to do yourself, just to kind of convince yourself of that this is sort of the right algorithm, if you will. So here you have 2 numbers of the equal sign, so you just this again is the sign bit up here. So 0, 0, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1. And you keep the sign since it's the same, and this in fact is plus 6, as you can convince yourself. Here, both signs are negative, so again, you can just copy the sign. And then here, add up the magnitude, so 0, 1, 1. And this in fact is negative 6, since this is the value here, 6. Okay. Now this is a little trickier, so now we have 2 minus 4, so 4 is actually the bigger magnitude, so that's the sign that we're going to keep. So the result's going to be a negative number starting with a 1, and then you have to subtract the 2 from 4, so you're going to do 1, 0, 0 minus 0, 1, 0. 0 minus 0 is 0. Here, 0 minus 1 is 1, carry 1. 1 minus 1 is 0, so this is 0, 1, 0. And this is, in fact, minus 2. But the issue here is, as you can see, it wasn't a particularly convenient way of getting to this result. So essentially I had to do this subtraction and reorder the numbers in some way, etc. Same idea here. The larger number is plus 4, so the sign is 0. But now I have to again do this subtraction. I mean, it's the same thing here. Minus 0, 1, 0, which again is 0, 1, 0. So this will give me plus 2, as it should. But the basic message on this slide is that even though sign magnitude is actually a really intuitive representation. So it's just first bit is the sign, and the rest you more or less recognize what the magnitude is of the number if you know binary numbers. The basic mathematics are somehow too complex. They're very counterintuitive, and in some ways for a computer it's not well, maybe not that important whether the number system is easy to understand for a human, but what's important is that it's easy to manipulate the numbers to do arithmetic. So now the question is, okay, can we come up with a way of sort of picking negative numbers such that addition works? And our idea is to say, like, well, let's just call -1 is, let's just say that -1 is 0 minus +1, right? So basically here, 0 minus 1, okay, is actually 1, but you had to borrow 1. 0 minus 1, 1, but you borrowed 1. 1, you borrowed 1, 1. And again, this borrowed thing, I'll just have to forget about, because there's a fixed width, like there's nothing I can do with this. So basically I'm just going to define that this value 1111 is -1. So what I want to convince myself of is that addition actually works. So when I'm adding -1 to 2, it should be +1. So 0 plus 1 is 1. 1 plus 1 is 0 carry 1. 0 plus 2 is 0 carry 1. This is 0 carry 1. Can't forget about this. And so this number is just +1. Okay, so it seems like this intuition that a negative number is just 0 minus the positive number might work out. And in fact, the number system that you arrive at when you do this is essentially called the 2's complement number system. What's interesting, in 2's complement, there's only one representation for 0 shown up here. There's actually one more negative number than there are positive numbers. And it's very important, we have to work with a fixed width format for both positive and negative numbers, right? So again, in some ways, the leading bit, the leading bit indicates whether you're dealing with a positive or a negative number, or positive or 0 or a negative number. And the rest essentially contains information about the magnitude of the number in some ways, but the encoding is much less intuitive than we've seen for the actual sign magnitude representation. Okay, so now the question we want to ask is, like, how do you generally go from a negative to a positive number in 2's complement? Okay, so this is going to be really important that you remember this little bit of information. So essentially what you have to do, the algorithm is that you take the number that you have, could be positive or negative, you flip all the bits and you add 1. Okay, so for example, if you want to negate the number 2, you want to get -2. Well, -2, according to this algorithm, is flipping all the bits of 0, 0, 1, 0 gives 1, 1, 0, 1, and you're adding 1 plus 1 is equal to 1, 1, 1, 0. And looking at this representation over here, you can see that -2 is in fact 1, 1, 1, 0. And so what you've done here essentially is you've started with the number +2 here. You've flipped all the bits, which actually gives you -3, and then you've added 1, and that gets you to -2. And now if you did this again, so as we've shown down here, so now if you want to negate this back, you just should get 2, which is 0, 0, 0, 1 plus 1, which is 0, 0, 1, 0. And of course, that's exactly what you want, right? So flipping the bits essentially got you to from -2 to +1, but now by adding 1, you're back to +2. And now the neat thing is that addition in the 2's complement formats is going to be really, really simple. So again, it's the same examples that we've seen a couple slides ago in sign magnitude, and we'll just go through them again. So here two numbers with equal sign, 0 plus 0, 0, 1, 1, 0. And this, of course, is plus 6. I mean, there's no surprise that with positive numbers, two positive numbers, everything's easy. Here, 0, 1, 0, 1, 1, 1, 0, 1, 0. Okay, so here, not obvious that we get the right result. Well, what can you do? You could essentially convert this back to a positive number. So you can say that this is 1, 0, 1, 0 is equal to minus 1, 0, 1, 0 is equal to minus, now remember, flip the bits and add 1, 0, 1, 0, 1 plus 1 is equal to minus 0, 1, 1, 0, and this is in fact negative 6. Okay. Here, 2 minus 4, just going to add again, 0, 1, 1, 1. That in fact is, well, okay, it's not obvious, but you can easily convince yourself that this is negative 2 by just flipping the bits and adding 1 to this. And then over here, minus 2 plus 4 should give you plus 2. And you get 0, 1, 0, 1, 0. Again, always drop the carry. And this is obviously plus 2. This is negative 2. So this is now really nice, right? Like previously when we did the sign magnitude additions, we kind of had to think about which number is bigger, subtract the magnitudes, keep the sign of the bigger, etc. Not very intuitive. Here, it's completely mechanical. Just add up the numbers and you get the right result. Subtracting in 2's complement is also, not surprisingly, quite simple to do. And it's essentially just saying if you want to do a minus b, well, just convert the subtraction to an addition by essentially converting minus b to, or representing minus b as b bar plus 1, so flip bits, add 1, and then it's very straightforward, right? So essentially here we want to do 0, 0, 1, 0 minus 0, 1, 1, 0. So let's just say that this is 0, 0, 1, 0 plus 1, 0, 0, 1 plus 1, which is equal to 0, 0, 1, 0 plus 1, 0, 1, 0. And you can do this addition. Let me just write it here, 0, 0, 1, 0 plus 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0. And then, of course, you need to convince yourself, so since this number here is 2, and this is minus 6, you should get minus 4. So you might want to check this by essentially doing, saying that this number here, the negative of it, should be plus 4, and that's 0, 0, 1, 1 plus 1. Oops, sorry. And that is 0, 1, 0, 0 equals 4. Okay, so that worked just the way we wanted it to. And you can do this with these other two numbers for yourself, but I think this is the nice thing here is it's extremely simple. If you want to do subtractions, a minus b, you just have to convert minus b, or you just have to essentially convert it to an addition where you do a plus minus b, and minus b can just be expressed by, represented by b flipping all the bits, adding 1. So this is extremely intuitive and sort of mechanistically simple to do. One other concern that we haven't sort of explicitly addressed yet is the issue of overflow, right? So you can easily, you're working here with fixed width numbers. So for example, in this particular format with 4-bit numbers where the leading bit is sort of the sign, if you will, I can only represent numbers from 0 or from minus 8 to plus 7. So if I have an addition such as 5 plus 3, I cannot get the right result, right? Because I'm adding I'm saying I'm going from 5, add 1, add another 1, add another bit, one bit, and I'm ending up at minus 8. So the output that I'll get will look like minus 8, and it's essentially the wrong result because I just can't represent minus 8 in this particular format. Similarly here, if I subtract, or if I do the addition minus 7 minus 2, I will end up with the value plus 7 if I just follow this circle. And of course this is the wrong result, and again it's just the direct consequence of the fact that I can't represent minus 9 in this particular format. So really the only thing that you can do to detect overflow is to sort of check whether you have overflow or not. You can't really you can't really know what the right answer is, but possibly you can figure out whether there is whether your answer is right or wrong. So the first observation is that overflow can only occur if the two numbers have the same sign, right? Otherwise you'll never get overflow. But still, it's not obvious whether you have overflow or not. So we'll look at sort of 4 different examples here, and then try to come up with a rule to figure out whether we have overflow or not. Right? So here, 5 plus 3 should be plus 8, but it's actually minus 8, so there is overflow here. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. And 1 plus 0 is 1, carry 0. Okay, I'm going to write that down here explicitly for now. Here, there's also overflow. Minus 7 minus 2 should be minus 9. If I just do the math, I'll get 1, carry 0, 1, carry 0, 1, carry 0. 1 plus 1, I'm going to write this 0 here explicitly, is 0, carry 1. Okay. These other 2 examples, there's no overflow. I can actually represent these numbers. So 1 plus 0, 1, 1, 1. 1 plus 0 is 1, carry 0. 0 plus 0 is 0, carry 0. And then the last one, and I'll show you in a second why I'm writing these carries so explicitly. So 1 plus 1 is 0, carry 1. 0, carry 1. 0, carry 1, 1, carry 1. Okay? So one thing you might observe, it's not entirely obvious, is that in the 2 cases up here, where you had overflow, the carry into the last bit and out of the last bit are different. While in these 2 situations where you did not have overflow, the carry into the last summation or last bit summation, the carry out of it, are the same. And so essentially what you can say is that, and this actually is generally true no matter what the numbers are, so you can say that overflow is in fact the XOR, the exclusive OR of the carry in and the carry out of the highest order bit. And so now that we have negative numbers and we know how to do addition and subtractions and we even know how to deal with overflow, I kind of want to show you one other slide, and this is actually one of my favorite slides in this lecture, which is how to build a subtractor, right? So this thing here looks extremely similar to the adder that we've seen before. And in fact, if I just connected all the inputs to the corresponding full adders, that's what I would get. But now I want to think about how I can get a subtractor instead of an adder. Okay. So the first thing to think about is essentially the following. So we said that going to subtraction or doing subtraction is really like doing addition. So a minus b is the same as a plus minus b, and minus b could just be seen as, or can be represented as b, where all the bits are flipped and 1 is added. So how do I do, so if I want to do subtraction, I somehow have to implement this sort of bit flip operation. Okay, so how do I do this? Well, somehow if I have a control input, okay, and it can take two values, 0 and 1, and let's say I have some other number, let's call it b here. Can also take the values 0 and 1. Okay. And I calculate the XOR of these two. So that would be 0, 1, 1, 0. You realize that essentially what I'm doing here is that if the control has the value 0, then the output here is just b. On the other hand, if the control has the value 1, then the output here is not b. So you could also represent it as a sort of shorter summary. You could say that control 0 and 1, the output is b or not b. So really what this is, it says like I XOR with a control input realizes sort of a bit flip operation, right? Okay, so that's so what I'm going to do is I'm going to say in order to do subtraction, so a minus b, I have to have some sort of control that I can XOR together with my b inputs. Let me redraw this. In such a way that whenever this control input is true, I'm doing subtractions, and whenever it is false, I'm doing addition. And of course I need to use the same control input for every one of my b's, because I want to flip all the bits of the number at the same time. So what I have here is a bunch of XOR gates. And for all of these XOR gates, one input is the control input. And the other input is b. And so if this subtraction operation, if subtract is true, then I'm basically flipping all the bits. Now I have to do one other thing, which is actually have to add a 1, right? I have to flip all the bits and add 1 to convert minus, to represent minus b. And here's how this carry in becomes useful, right? In previous, when we just designed an adder, where we just looked at positive numbers, we said, well, this carry in, we don't really need it. We're just going to set it to 0. But it's convenient to just use full adders everywhere instead of just making this explicitly a half adder. But now we could say that if we're subtracting, then if subtract is true, then this plus 1 can just this carry in can just be the value 1, which gets fed in here, and that's kind of like adding 1 to this number, which is exactly what we need to do. And then of course everything else kind of stays the same. So you have these carries that ripple through, you have the A inputs that get added here through these full adders. And then the last thing that's also kind of interesting is that we've talked just on the previous slide about how we can deal with overflow. So we have here one other output, and we said that overflow is essentially the XOR of the carry into the last bit and the carry out of the last bit. So we're just going to add this here. And now we've essentially designed a system that really does addition and subtractions as needed. If I set subtract to 1, then I'll do a subtraction. If I set subtract to 0, it's just a standard adder. And then it has this additional feature that I can sort of check whether overflow occurred or not. I'm going to skip this slide, but I think it's, you want to convince yourself that you can sort of convert decimal numbers to 2's complements and back. So you kind of want to just be comfortable with 2 complements numbers. Same here. So here we're converting from 2 complements to decimal. Again, just practice this for yourself. This is can be practically important sign extension. So to convert from an n bit to an m bit 2's complement number, where n is smaller than m, you can simply duplicate the sign bit, right? So convert. So for positive numbers, this is very intuitive. You're just going to say if you want to convert these 4-bit numbers to an 8-bit 2's complement numbers, you just add a bunch of zeros. Right, so this is obviously true. What's maybe a little less intuitive is that if you have a negative number, you can add leading 1, so 1, 1, 1, 1, 1, 0, 1, 1 is actually the same number as 1, 0, 1, 1. And to convince yourself of that, what you should do is you take these 2 numbers and convert them both to a positive number by flipping the bits and adding 1 and convincing yourself that they are the same positive number.